Welcome to our repeated measures analysis of variance, or ANOVA. This should just be a logical extension from our more detailed introduction to ANOVA, except that there we covered independent or between subjects measures. And this time, just like for a t-test, we are making the transition to repeated measures or within subjects designs or dependent samples. So all those words kind of go together. Within, repeated, dependent. And so all of those situations describe data that we have two means or more that we're comparing, and we have multiple measures from the same person at time 1, time 2, time 3. And of course with t-tests we're stuck with two means, but ANOVA, it really opens up a virtually unlimited number of means that we can test. Of course, practically, we don't want to test a million means against each other, but there's no theoretical limit to what we could do with the ANOVA framework. So first of all, here's a brief overview. Since we've covered and introduced a lot of the ANOVA components in the previous slideshow, this one will go by, I think, a little bit faster. We don't have to describe the new F table or the F distribution. We're still going to be using those. We just have slightly different ways of figuring out our degrees of freedom, and our formulas have to look a little bit different when we move from independent data to dependent data. So first of all, let's just introduce what the repeated measure ANOVA looks like and why it's necessarily different in some ways, but not most ways, from the independent samples we have previously covered. Basically, repeated measures ANOVA uses a single sample and exposing them to a treatment multiple times or multiple treatment conditions. Usually that is representing some sort of change or development over time. And it's just a matter of how many times have we repeated the same measure. So that clearly explains to me why we call it repeated measures. We call it also within subjects, because unlike an independent subject design, each person only has one measure. Repeated measures within subjects means you have multiple measures that you've provided yourself. And across the different times, I can link your time 1 to your time 2 to your time 3. And that's going to lead to a clear advantage, we'll find out, in terms of understanding some error that otherwise we can't really, is not there to understand for the independent samples design. So basically, the hypotheses for the repeated measures analysis of variance are exactly the same as the independent measures ANOVA. Basically, null hypothesis is that there is no difference between any of the time 1, time 2, time 3, or however many more populations there are. And the alternative hypothesis is that at least one and potentially more than one of the means is different. We also have the idea of the F ratio, which is structured conceptually in the same way. Basically, our F is the between treatments versus the within treatments. So note it's not between groups anymore, as it is with the independent groups model. This is, we have different treatments, the same people in each treatment. How much change is there or difference between the treatments? But of course, there's also difference in scores within the treatments. Why aren't people exactly the same within the treatments? There's variability. It's within. We can't explain it due to the conditions. It's just there, and it partly serves as a little bit of error that we have to factor in our significance testing. So basically, ANOVA is, as I mentioned before, a partitioning of variance model. And basically, we're doing the between and within partitioning. But for within subjects or repeated measures, we can subtract out that variance due to individual differences. So we're going to introduce a new term here called between subjects. So just think of the source table for the previous independent measures ANOVA, and you can think about how we had our total, sums of squares or variability, and then broke that down into the between and the within. Well, our source table for the repeated measures just adds a new component or a row in our source table that's going to be labeled between subjects. So we'll find out how we do that and continue to explain why we can do that with this design. So of course we're going to have to review some formula, but also introduce some notation and formulas that are slightly different. I wouldn't say any more scary, just a little different. So we already know these basic components. This is a complete review from the independent measures ANOVA, or between subjects ANOVA. So of course we can review the total number of, instead of groups for between groups, now we're looking at conditions. Our within subjects or repeated measures is the number of conditions, or the number of times or treatment times that we administer. We still have in each time, little n, we have n total, the number of total, in this case, observations, not total people, but let's say we have 5 people and 5 times. That means we have 5 observations of each of these 5 people. That's our big N. And then our T and our G essentially function the exact same way before. Sigma X for within each treatment instead of within each group. Now it's within each treatment for repeated measures. And then we have our grand total for the sum of all the raw scores. Now, what we also want to consider is this P, as we're going to find out the total of all the scores within each individual. And we'll see that, well, as an individual difference, sometimes people just start higher and they continue to be higher from the very start through the very end across the treatments. So that is something we know about that person. They start higher than the rest, or somebody who starts lower than the rest. And instead of just treating that as they haven't changed any differently than the other people for the most part, but they started higher and ended higher, that's an individual difference that we can draw out some of that. We can draw out some of the meaning of the scores because we know we can connect them. So that's our P, is information about a person. That's an individual difference that we can't do with our independent measures. So we'll see this, how we get to the P in a little bit. But basically, if we think about a running example, person runs a race 3 times in 130 seconds, 180 and 192 seconds, we would add these together to get the P total. And again, if these are independent measures, we can't add them together across groups in an independent design. They're different people. But since it's the same person, we can get this new meaningful measure linking scores across treatments because we know they're from the same person. So this is extra variance that we now have that we wouldn't have with a independent measures or between subjects design. So the formulas are basically the same, except in this time we have our new between subjects variance, or before that we get to our sum of squares, another measure of variability. And we can have a dependent measure of motivation, and then we have the different times, 4th grade, 5th grade, 6th grade, and now we have students. These are people, and we know that, these aren't independent groups. We're not comparing one group of 4th graders to 5th graders, and it wouldn't matter that Johnny in 4th grade, there's no way to tie his score to Susie in 6th grade or 5th grade. It doesn't matter the order of these if they're independent. But now, since it's repeated measures, we know there's dependency in these numbers, and that dependency is these 3 scores correspond to this same person. And so that is something we can come up with about these 3 scores, combine these 3 scores together in a way that we couldn't with the independent measures design. So if we're looking at our basic, somewhat hopefully familiar ingredients for the pieces we need, we have raw scores, and then for each group, or in this case treatment or time, we still have our T, calculate the sums of squares, but hopefully they're given to us because we don't want to have to get our mean and standard deviation. Let's just have it given to us and we can deal with this. We can start here. But of course, then we have our group size. In this case, though, how many people in a different condition or treatment or time. We also have our K, the number of times, 4th, 5th, and 6th grade, G, and then of course, we don't have to calculate this, but sigma x squared is a number we need for our formulas. So basically, we're carrying out the repeated measures ANOVA in 2 stages, which is first, exactly like what we've done with the independent measures, but now we introduce what's known as error variance because we can subtract out from our within treatments variance this between subjects variance. Why are some people starting high and ending high from 4th to 5th and 6th grade? That's just an individual difference that they came into the study with. It wasn't caused to change over time. They still can change, but the being at consistently higher levels is a consistent factor over the times. But since we know we can link those numbers together, we can then say we understand that variability and can take it out of the total within treatments variance. So of course then we need to calculate the sums of squares and degrees of freedom for those 2 components as well. So here is our source table for analysis of variance, and as before we had our between and within components, each with sum of squares, degrees of freedom, leading to a mean square. But before we would get a mean square of within for our independent measures. But now with our dependent measures, we can divide this within into our between subjects, which we understand, and we don't treat as error anymore. We're just going to partition it, identify it, and then take it out. And what's left over is what we call error. It's variability that we still can't explain. We can't explain based on individual differences or between subjects factors that's consistent over the times. This is differences within groups that isn't changed by the treatment or the times. So it's variability that we can't explain either by the treatments or by knowing linking scores in the different times together in the between subjects factor. So you can see this is going to be the denominator of our mean square, what we used to call within, but now we've subtracted out this between subjects, and now we have a smaller error term if we have data that we know is truly a within subjects or repeated measures or dependent samples design. So I know there's lots of numbers on here, but there's only a couple things here that we haven't done before. So basically, all of this is exactly what we saw from the independent measures T. Now we just have our P's, which is adding up the raw scores for person A, their time 1, time 2, time 3, and we get a P of 8. And of course we can square it and get a sums of squares and other P values that we might need. If we look at our formula for our between subjects, basically for each person, 1, 2, 3, 4, 5, we have 1, 2, 3, 4, 5 versions of using this P squared. So this is how we're taking our within subjects formula from before, and then identifying or isolating the between subjects variability so that we can just subtract it out. And here's the subtraction. Our within treatments or our within variability that we can't explain. Well, now we can explain the between subjects or individual differences part. So now what we're left over with is the error. But the sum of squares total and the sum of squares between is essentially figured out the same way. So for example, sum of squares between formula, we have these different T's. We have 3 times, and so we'll need 3 versions of this part of the formula, and then we tack on our g squared over n at the end here. So these are the formulas for how we get to our values for our important components of our source table. All of these formulas are essentially trying to find the variability, sum of squares components for our source table. So a couple things to keep in mind as we're thinking about degrees of freedom. We're going to have to keep that in mind. So in case we're still having trouble distinguishing from the independent to the dependent, the big N is still the number of observations, just not the number of participants, because we have multiple observations of each person, or an observation of each person at each time. But still the number of observations is still that big N minus 1 for our degrees of freedom for total. Degrees of freedom between treatments is pretty much number of treatments or times minus 1. And then our degrees of freedom within becomes n minus 1. And there's a sigma, so we got to have n minus 1 for time 1, n minus 1 for time 2, n minus 1 for time 3. Another way to think about that is just big N minus k, whichever one makes more sense to you. So big N minus the number of treatment times. And now we have our degrees of freedom between subjects. This is the new component, basically our N, or our number of people in the study, minus 1. So for the example we've been working with, we have 5 people in the study, 5 people at 3 times each. So we have 15 total observations, our big N, but the number of people minus 1 gives us our degrees of freedom for our between subjects factor. And then of course we have our degrees of freedom error, meaning degrees of freedom within minus our degrees of freedom between. Now the nice thing is, with your source table, you don't need to calculate all these. If you get enough of them, by logic you can infer, or working backwards sometimes, what the other value has to be. So we'll go through some examples of those as well. So then we just need to get to our mean square. When we'll run through another example where we go through this in a little bit more detail, but the idea is we need to use those formulas and get our degrees of freedom so we can get our mean square of between. This is our top number in our F ratio, right? That's how we get this number, 20. Over what, though? And it's not just mean square within, like with the independent measures. We've subtracted out the between subjects variability that we know we can account for. It's not just random anymore to us. So what's left is random, or error that we can't explain due to our treatment or the between subjects aspect. And we get our mean square with plugging the values in, and then pop that into the denominator of our F ratio, and we see a really big treatment difference. So the means between the times are clearly very different relative to the error, gives us a gigantic F. Now, we actually do need to look at the critical regions and consider our alpha values, but more than likely, in any case, this 24 F ratio is going to be significant. So let's just run this through the hypothesis testing. And just repeating how we set up the null and alternative hypotheses. No difference between the population means at different times. At least one of the times is different significantly from at least one of the others, but maybe more. Then we need to think about our critical region. And remember, degrees of freedom between is the same. How many times are we considering? Well, basically 3 different times minus 1 gives us degrees of freedom between of 2. So we look at that for the column of our F table, but what row are we going to look at? Now we need to consider degrees of freedom error. So we've already calculated that. and that will tell us our F ratio, our critical value. So that means, assuming we went with the alpha 0.05, our F has to be higher than this for us to reject the null hypothesis. And notice when we report our F, we also include the degrees of freedom that we used. So first of all, the first report is going to be the between. That's always first, and then comma, either the error for the repeated measures that we're doing now, or the degrees of freedom within for the independent measures, analysis of variance. So of course the between first, and then the error after that. Or if you want to think about it, degrees of freedom numerator, comma, then degrees of freedom denominator. So then we actually plug in our formulas where needed. We get our source table, our sums of squares, our degrees of freedom, our mean squares, and we find that the F is 24. We find that our 24 F ratio is much greater than our critical score. And so we reject the null hypothesis. And we say that there is a significant change as students progress from 5th to 6th grade. But we can't say which mean is significantly different. Now we can go back and look at our raw data, and I think there are some clear hints at what might be significantly different. Usually the biggest difference in our means is going to be significant if we get a significant result. It's just a matter if there are other differences there that we're not sure about. So let's look at some of the costs and benefits. Hopefully this will be a little bit of a repeat compared to our discussion so far. Now the idea is a repeated measures design is a little bit more powerful because it can remove that individual difference or between subject variability. It also reduces the possibility of the type 2 error, which is essentially failing to reject when actually we should have rejected, we find out later on. It also means you just have to have a smaller sample size, so you use fewer subjects than the independent measures design. But the problem is there's a possibility for carryover and progressive effects, as we covered in the repeated measures t-test. So if there is a change or difference that's not due to the time, but instead due to participants either getting tired or figuring out the questions and not actually getting better at the construct, but just responding better to the specific questions you've asked multiple times, that's a problem. Also, you have to consider repeated measures design. You're asking subjects or participants to be involved and provide data at more than one time. There's always a great chance that for whatever you started with, you don't have all those people come back for the second or third or however many more times. So you can start to have attrition of data, especially with the more times that you include. So let's also talk about some assumptions of the repeated measures design with the analysis of variance. Once again, we have independence of observations. So again, we're not looking at individual scores when they're really working as a team. We're assuming that they are not helping each other out, that they're not dependent or getting the right answer just because one person has shared it with everyone else. That would really violate this assumption, and if we suspect our data looks like that, we shouldn't even run the analysis. We also think that the populations from which the samples are selected must be normal or close to normal. No super skewed distributions in which, for example, most people are on either a high or low end with just extreme outliers. We also, again, assume that the variances are equal homogeneity. We assume a similarity of variance between the times. So again, you can't have so many times that, for example, people start and have a nice variability in test performance, and then by the 5th test, they're all getting 100%. That means they're not necessarily learning, in the way that we probably think they are. It's probably a problem with that last measurement, that there's no variability anymore. And then finally, we have the idea of the homogeneity of covariance. So for example, we're pulling out variability due to individual differences, assuming that some people come into our study ready to respond better to our medication or our treatment. Some people come into it ready to respond more poorly to our treatment or our medication, and assuming that if they start out high, they stay high for time 2, 3, and 4. They don't have to raise or lower their scores over time at the exact same slope or rate of change than the others. We don't want somebody, though, being the highest in terms of outcome at round 1, and round 2 they're the lowest, round 3 in the middle, and then back to the lowest. That really violates this covariance, and it's going to hurt our actual likelihood of significance anyway, but it might look for us to explore some other artifact outside of what we think is going on in the study that's actually causing a lot of bouncing around that changes relative standings of people throughout each time. So problem, if you see that, it's an easy spot check to look at person X, person K, and see if they're largely in the same relative position to the other people for each time. And then finally, we'll wrap up with effect size. So here we are with our eta square again, and we have two ways to get to our eta squared, depending on which is your preference. So first of all, we can have sum of squares between. That is our numerator for both versions of our eta squared. And then we just take, for this first version, our total sum of squares and subtract out that between subjects that, since it's repeated measures, we can identify as individual differences. It's not a treatment effect, but it's because of the individual difference and we understand it. So it's not part of our total variance that we care about. We can also get to that same value by, again, starting with the same numerator, but we take our between treatments and then the error. So really, if depending on which values you choose to use to pull out of your source table, you'll get the same eta squared. Now, that's all I have to say about the repeated measures analysis of variance. I know that some books don't cover this in as much detail, and really I'm not looking for someone to start with raw data and be able to work through entire problems all the way till the significance test, but I do want to be able to pull out parts of a source table and have you be able to figure out what the degrees of freedom for a different component would be, use those degrees of freedom to find a proper critical or cutoff value in the F table, and also know what the different pieces of the formulas are. But again, working from beginning to end is not necessarily the goal, because there's a lot of steps and things get a little bit more abstract for ANOVA compared to some of our previous statistical tests. So hopefully all that's making sense and you're comfortable with the ANOVA landscape, both for this class and maybe interested in, if you're exposed to future research with more complicated designs, thinking, how would they do that in the analysis? How would they enter that in the statistical software? What would they consider as far as a 1-factor versus 2-factor, and how many levels of a factor? So this is why analysis of variance, once you know the basics, it opens your mind to how it might be used by researchers using the same formulas, but for a lot more complicated applications. So once again, hope you're comfortable, and we'll be moving on after this to even more useful examples in some cases of statistical analysis.